Hello everyone, today I'm going to be giving my presentation, Material Properties, a case study. Overview. First, we're going to give an introduction on what's the difference between a mineral and a rock. Then we're going to talk about the property of hardness itself, a little bit about crystal structure, a little interesting experiment of hardness versus density, then a physical experiment, and then I'm going to conclude. And this mineral is tourmaline, by the way. So aren't minerals and rocks the same, right? I doubt many people have heard what the difference is between them, and I'm going to outline that here. But first, the study of geology is divided into two categories. Mineralogy is the study of minerals, and petrology is the study of rocks. The difference between a mineral and a rock is that a mineral is a naturally occurring substance with distinctive chemical and physical properties, a composition, and atomic structure. A rock is also naturally occurring, yet they are mixtures of minerals. So we'll see how that plays out in a minute here. This mineral shown here is calcite. The physical property of hardness. Hardness is the resistance to a permanent deformation. The Mohs scale of hardness is a measure of hardness, and it goes from 1 to 10, 1 being the softest and 10 being the hardest. This mineral right here is corundum. Corundum has a hardness rating of 9, making it one of the hardest naturally forming materials on planet Earth, second to diamonds. For example, I'm just going to provide an example of a mineral, olivine. Its Mohs hardness ranges from 6.5 to 7, so sometimes they can range. And this one has an orthorhombic crystal structure. And because it's a mineral, it only has one type of crystal structure. Whereas a rock, it doesn't really have a crystal structure, at least one that you can give it a name, because it's an amalgamation of many different structures, presumably. And every mineral has a unique crystal structure. This is fluorite, by the way. Up next, I'm going to show a very nice picture of a mineral that I'm sure a lot of people have heard of before. And I'm very proud of this picture I took myself, showcasing the crystal structure of pyrite. As you can see, this is a piece of pyrite. Pyrite has a very similar color to gold, but it has a much different kind of a structure, which I tried to showcase here. Very, very up close image that I took myself. Here I'm going to give an example of one of the rocks that I did in my case study, pyrite, I just showed. Pyrite has a simple cubic crystal lattice, and pyrite's chemical formula is listed here. This is a picture of what the crystal structure looks like for pyrite up close. This is just an image showing what it would look like as a mixture of iron and sulfur. Now here's the piece of my experiment which I did as a research experiment, comparing the hardness and density between minerals that have the same crystal structure. Because a lot of people have a misconception out there, which is the density and hardness go together. And here I'm showing that they really don't. It's not a very good correlation. Here I took about 20 minerals that I have at my disposal as part of my case study. One group of about 10 here are monoclinic, and another group of about 10 are hexagonal. And as you can see, conflicting evidence that does not really suggest that density and hardness go hand in hand. As you can see, for hexagonal, it looks like the opposite. For monoclinic, it looks like it's true. I believe that the answer is that there really isn't much of a correlation. It may be a slight correlation. Here's another example of the data. These 10 data points are going to be from my study, or from my experiment rather, my scratch test, which is coming up. Scratch test experiment. Here I've gathered 10 specimens. They range from 1 to 9 for hardness, 1 being talc, 9 being corundum, which I showed earlier. And I'm curious what will happen when you scratch them. And here are the specimens listed out here. My hypothesis, right? So I'm going to be using a copper penny to attempt to scratch these minerals and rocks. And I'm trying to see what happens if you take something, and scratch a varying set of hardnesses. So I'm using one hardness level and seeing how other hardness levels will react. So my hypothesis is that the copper penny will be able to scratch the minerals or rocks up to a Mohs level of 4, while it will be scratched itself by those higher. The reason I chose this is because a copper penny has a hardness of 3.5 on the Mohs scale of hardness. The rock shown in this picture is obsidian. So here are my results. And here's a picture of one of the scratches left by that penny on talc. This is the softest mineral there is. So the copper penny was able to scratch 3 of the 10 rocks. These 3 were the softest: talc, alabaster, and calcite, in that order. Everything else harder was not scratched. Although, I have to note that when I scratched some of the harder rocks that were a little flakier, some of the flakes did come off, but that's not exactly a scratch per se. But I will list that as a point of possible confounding variables. So to recap, all things that were harder than the penny were not able to be scratched by the penny. And in fact, those rocks scratched the penny. The penny was very, very much deformed by the harder rocks, especially as you got harder. So in theory, this would apply if I were to take corundum, the hardest rock mineral, to scratch everything else. It would. And in fact, I did scratch some of them with corundum. And with pyrite in particular, I made some interesting scratches and even came off a lot of dust. The way that you can tell the difference between pyrite and gold is the color of the dust. The color of the dust of pyrite is black. The color of the dust of gold is also gold. To do a recap, first I talked about minerals versus rocks. Then I talked about the physical property of hardness, crystal structure, density versus hardness. Found out that they're not really all that correlated. And then a quick fun experiment to showcase how hardness is a physical property in the real world. Thank you very much. Have a great day.